All right, so welcome to the introduction on logs. Okay, so first in this video, I'm just going to introduce and kind of talk about what does log do. Now you might have seen log and also ln, which is ln, on your calculator quite often, okay, if you've ever explored a scientific calculator and you wondered, what does that actually do? Well, so in order to explain it, I'm going to try to talk to you and show you some examples with regards to exponents, because a lot of people understand exponents as they learn about exponents a little bit earlier on. So when we're talking about exponents, we have a base and then we have an exponent. So if you're seeing here on the screen, what I have done is I have an input into a system, and that particular system just says it is base 2 and it is raising the input, which is x, okay, and that is your exponent. And then your output is simply y, which is equal to 2x. So if I have my input x and I start throwing in some numbers into this, I obviously will get an output y is equal to 2x. Let's try it with some examples, and then I'm going to graph it for us. So here, notice, okay, so on the left-hand side, I have a table of values, and I'm going to just kind of arbitrarily just say, okay, so imagine my input was -2. If I put -2 into this system, then that means that my output is going to be 2 to the power of -2. And that will be just 1/4. Because 2 to the exponent of -2 is basically 1/2 to the power of 2. Now, if you don't remember some of the exponent rules, I'm going to put a link up above and you can refresh yourself on all the exponent rules. Or you can try to use your calculator, right? So you can just take your calculator out and you can say 2 to the power of -2, and then you'll see that it is 1/4 as we have it. So now that is my answer, which is really 1/4 or 0.25. Now if I graph this, so I'm going to try to graph it here. So let's imagine, so this is my -2 right here, and it says it's 1/4. So if this right there is 1, then that is 2, 3, 4, 5, 6, 7, 8, and so on. All right, so this would have been -2, that's -1, 0, and then 1, 2, 3, 4, 5, and again, that continues. So I could graph this, and I'm going to zoom in here a little bit just so that it's easier for me to graph. So 1/4 basically would have been, I'm going to take a different color just to plot it. It would have been somewhere, okay, around here, 1/4 right here. Because notice that that's a 1, so that means 1/2 is one of those squares, and 1/4 is half of that. So that is my first entry. Now I'm going to continue this just to show you what is actually happening with these exponents. So here's -1, and this is going to be 2 to the -1. And again, you can substitute this in, and you'll notice that this will be 1/2. So my output would have been 1/2. So now if I plot that 1/2, okay, at -1, so that's going to be right here. All right, so I have that. So I have 2 points, and it doesn't seem like it has grown much. Now my next input, I'm going to put 0. So this is 0, so this is 2 to the power of 0, or the exponent 0. And that's going to be equal to 1. Again, that's just an exponent, okay, rule. And again, you can go back to those links. I can provide a link here, what happens and why it happens, okay, when you have an exponent of 0. So you can check that out. And this is just equal to 1. So I'm going to put that in here. So notice it crosses the y-axis, so that seems to be my y-intercept, and it crosses at 1. Now, right away you're noticing that, this doesn't look really like a straight line anymore. Okay, it seems to be kind of going up. And notice it's growing by powers of 2. Okay, it has a factor of 2 every time. So from a quarter, if you multiply a quarter times 2, it went to a half. If you multiply the half by 2, it goes to 1. And now we can continue this kind of table of values. So here, if I put in 1, I'm going to get 2 to the 1. And this one, okay, you will know that this is just 2. So I'm going to plot this up here. And notice that, oh, okay, so that has grown now. Again, it has doubled. And we can continue this trend. So this is now 2. This will be 2 to the power of 2, which is 4. And if I plot this, so now 2 and now 4, notice, oh, okay, this really is starting to skyrocket on us. So it's going kind of nicely slow, and then boom, it's starting to explode. It's growing really quickly. Now let's put one more. I know that the table doesn't have a place there, but we'll put it anyway. So 2 to the power of 3. And now, okay, well, 2 to the power of 3 is just 2 times 2 times 2. And that would be 8. And so for that, you know, I can plot this up here. And 8, okay, so now it's really taken off. So if I try to do 4, it doesn't even fit on this, because it would have doubled. It would have went to 16 and then to 32. So you're noticing here that if I tried to connect these, okay, so it would have looked like, I'm going to give this my best shot here. So it's going to be looking kind of like this. All right. And of course it keeps going, and it keeps going in this direction as well. That definitely doesn't look like a straight line. So this is not a linear, okay, relation where we're just having a straight line. This looks like it's growing. And that is the plot of y is equal to 2x. So we have a base of 2, and notice that it started to blow up on us. So that's the first thing I wanted to introduce. And this is something that you can try, and you definitely can see that happening. Now, notice the kind of beauty here, and I'm going to show you using Desmos, which is a great tool, which you can go on. And I'm going to plot this for us fully. This was 2 to the power of x. And notice how it just explodes upwards very, very quickly. So as x keeps getting larger and larger, it just starts to explode. So here it was going through 8, notice at 3 there, and then at 4, notice it has gone to basically 16, okay? And then it just keeps blowing up. Now, if I go back here, I want to show you another example with kind of this whole input and output, and showing you these exponential growth. And I will tie it back to logs in just a moment, but this is just an introduction, just so that you get a feel of what happens with these exponents. So next, what I'm going to do is I'm going to put inside, so this was 2 to the power of x. Now you could have put 3 to the power of x, 4, 5, or any number, 3.2, 8.5, doesn't matter. But now what I'm going to do is I'm going to set the base, and I'm going to make the base less than 1. So let's imagine, okay, so I'm going to try to set this. Let's say I put this at 1 over 2, and that is now my base. And I'm going to put my input, which is going to multiply, all right, as an exponent. Okay, it's going to be an exponent for this base of 1 over 2. So what happens in this situation? Let's take a look and see. So I'm going to try exactly the same thing. So I'm going to try it for -2. I'm going to try it for -1. I'm going to try it for 0. I'm going to try it for 1. We're going to try it for 2. And then we'll see if we need 3 there as well to try to get a gauge for this. So in this case, what I have is I have 1 over 2, and this is to the -2, what does this equal? Now, you can substitute this back in. Again, you can take your calculator out if you like. So I'm going to put this in brackets. So let's say 1 over 2, okay, in brackets, and I'm going to put an exponent of -2 on this. And you're going to see that this is equal to 4. Again, that just comes from exponent rules because it's negative. So it will turn the base into 2. All right, and we have a 4. So in this case, okay, we're going to be starting off, so at negative, so this is at -2. So now -2 was right here. And if we try to plot this, okay, it equals to 1, 2, 3, 4. So this, we're actually starting right here. Now, if we substitute -1, so I have 1 over 2, -1, you will notice that if you do that, you're going to get 2. You basically will half your previous answer. So now, all of a sudden, so at -1, this goes to now 2. At 0, so the input of 0, if we had that for x, so if we take this, again, anything raised to the 0 inside of the brackets is going to give us basically 1. So this now will cross through here. And I can continue this trend, so 1 over 2 to the 1, notice that's just a half. So now at 1, it goes to a half. And then here, 1 over 2 to the 2 will go to 1 over 4. So now this is getting smaller. Now if we did 3, it would be half of a quarter, which would have been 1/8. So what's happening now is this. Now all of a sudden, we're decaying. Okay, we're getting closer and closer to 0, all right, as this kind of comes down in this direction. So that's the first thing that I wanted to point out to you. So it turns out that if our base, so if we have, so this is for our base. So whatever our base is, so if we have y is equal to some base b with the input x, it actually is important to know what b is. And for the first case, where we had b which was greater than 1, then this explodes, all right? This is an exponential growth upwards. So this grows exponentially when b is greater than 1. And we had b is equal to 2, and we saw that explosion happening, okay, as x was getting bigger and bigger. Again, because it's an exponent. So we have a factor which is just multiplying consistently. Now, if your b is actually less than 1, now we're going to keep b because it's a base, so you're going to keep it bigger than 0. So if it's between that range between 0 and 1, then this starts to decay exponentially. That's what we saw here. So as x gets bigger and bigger, it starts to decay downwards. So this should give you some kind of a feel, and I encourage you to try to plot it and see it for some other bases, and then see the exponential growth as it takes off, or the exponential decay as it comes down as x is growing. So now, how is this being tied into logs? Well, if I took, so for instance, if I'm going to take this, I'm going to copy this right here. So let me copy that down. And I'm going to paste it right there. And what if I asked you, so now instead of this, all right, what we try to do is we try to reverse this back. So we're trying to go now, what if we knew what the output was? All right, so what if we knew what the output was here? So we know what the output y is, but we didn't know what the actual input was. So we're going in this direction now, trying to figure out what our input is. Now, in our table of values, so if I'm going to take this table of values here, I'm going to copy this down. So copy. I'm going to paste it right here. So let's say if this was our table of values right there. So what we're trying to do is, if we know the inputs, so if we know these, if we know that, if we know that, if we know that, and so on, we know that our system is 2x. Can we figure out what x was? Now, of course, we can figure out here because we can see it from the table of values. But what if it was taken away? What if we didn't know any of these values and we wanted to know what the exponent is? So basically, what we have is, so we have something like this. We have the output and we do not know what the input is. So if we have 2 to some x, all right, so if that is equal to that, equals to some, let's say, output 8. Now, if you're looking at this, you know, well, 2 raised to the power of 3 is equal to 8. So I know that. You're correct. So in this case, x is equal to 3. So basically, we're trying to figure out what this exponent is. Now, we can take other values as well. So what if we had something like this? 3x, so our base was now 3. And here, let's say that this was 9. Well, you would say, oh, that's just x is equal to 2. And you're correct. That's exactly it. So what we're trying to do is we're trying to find out what the exponent actually is. But how do you do that? In these two cases, it's relatively simple because the numbers are small. But what if the numbers were very large, or what if they were very awkward? For example, what if you had something like this? 1.7x equals to 11.2. Well, good luck trying to find what the exponent is there. You can keep guessing to try to see, but is there a better way than just guessing these numbers? And that is where we use log for. So log, I'm going to explain it, let's say from here. What log is doing, log is trying to find your exponent. So we take our base, so here is our base of 2, and we write it, so mathematically we would write it like this. This is our base 2. Our answer, okay, was 8. Sometimes we put it in brackets, all right, so sometimes we'll put it like this. And then we ask ourselves, all right, what is the exponent? So logs are doing nothing else but simply taking a base with your output y and trying to find out what your input, what your exponent actually is. And if I take out my calculator here, now here my calculator actually has several log functions there. So notice, you see log x, log 2, and log. Not every calculator has it. Most calculators will only have log, or they will have ln, all right, which is a natural logarithm. So those are the only two that you might actually see somewhere. So you can use either or to try to find what the answer is. Now here, so I have this log. Notice my base is 2. And here in my output, so that would have been 8. And if I hit equals, notice it gives me what the exponent actually is. And the same thing would have happened in the previous one. So if I took now the other example, so let's say if I took this one and I wrote it down, so log 3 of 9 as my answer. So if I take log, all right, and I'm sorry here, I used the wrong one, log of 3, and this is 9, notice that it gives you the exponent back, all right? So this was 2, and here the answer was 3. So that's what logs actually do. So logs are basically the inverse to try to figure out what your exponent is. And the way that we can write these logs is the following. We have, if you can write, so you can say 2 to the x is equal to, let's say 8. This is the same thing as writing log base 2, the answer 8 is equal to x. That is equivalent. And this is true for any base and any output. Any base and any output. So if I generalize this, then I could write simply whatever your base is raised to an exponent is equal to some answer y. This is the same thing as saying log of base b of your output is equal to your exponent. That is equivalent. And you can keep trying these, okay, and going back and forth in between. So for instance, in this example that I wrote here, if I had that and I wanted to find out what my x is, so notice this would have been log whatever your base is, which is 1.7, of your answer, 11.2, and that will give you your exponent. So if you do that, I can bring the calculator over on the other side. Let me clear this. Log of base 1.7, 11.2 equals, and notice that this exponent isn't as nice. It's 4.55, 29, and so on, because it's not always a pretty exponent. And we can check this. So what we can do is we can say, let's check it, 1.7 to the exponent. So that was 4.5529, and I'm missing some of those digits there. But notice 11.199, so as you can see, rounded would have been 11.2. So that's what a log does. A log just finds what the exponent actually is. Now here is the catch with all of these logs. Unfortunately, you may not be as lucky to have an app which allows you to put the base in your log there. So notice it's waiting for the base and I can put the base in. Most calculators will only have this log function, or they will have this ln function. You can use these to find the answer as well. So instead of inputting it as I did, so for instance, I'll give you an example. If you wanted, so we wrote log base 2, all right, of 8, we knew that the answer was 3. Now in your calculator, this can be written as simply log of whatever your output was divided by log of 2. And that will also give you the correct answer. So if you do not have the function with the base, then you have to use the log or the ln function and it will give you the same thing. So for instance, if I put log 8, now divided by log the base 2, notice it gives you 3 back. So I encourage you to try it on a few examples, right? Just to see. So how you would actually solve this. So here is one for you. So here's an example. Let's say we wanted to find, say this was 3.5, x is equal to 15.2. How do we find our exponent? Well, in order to find the exponent, so notice we have to change this to log of our base, 3.5, of the output is going to give us our exponent. Now, because we may not have this on our calculator, then we have to say log 15.2 divided by log 3.5. And that will give you your exponent x. So you can try it. Log 15.2 divided by log of 3.5 equals, and that's your answer. So it would have been 2.172234 and so on. You can keep as many digits there as you like. All right, so let me clear that and let's check it. So that was 3.5 to this exponent, and let's see if we're going to get 15.2 back. So 3.5 to the exponent, 2.172234, and I mean it continued on. And notice 15.1999, of course, because we didn't keep all the digits. So that's what you use logs for. You use it to try to find out what the exponent is. So this is the introductory video, and I'm going to continue. I'll do a few more on how to use logs and how to find exponents, how to solve for unknowns. All right, so see you in that video. Thanks for watching. Bye everyone.